Hello everyone, it's December the 5th. Alright, so we will first do this, and then we have to do this one more time, but now using BFS, using DFS. And then finally, let's see what is this problem is about. Alright, odd, even, linked list. Given the head of a singly linked list, group all the nodes with odd indices together, followed by the nodes with even indices. I've done this before. And return the reordered list. The first node is considered odd, so that's 1, right? And the second is even. And that the relative order inside both should remain as it was. You must solve the problem in O1 extra space and O(n) time complexity. So basically, we can let me think. So that's the start, right? And now basically we just delete, right? We delete and delete. Yeah, every time we delete this, But after you delete, you need to put this somewhere else. So we have a temp, right? A dummy node. And then every time we delete this, we just put it in a dummy node. We delete this, we put in a dummy node. And when we loop, when we have this is the start, we delete the next and then link these two together. Yep. Let's do this. Well, I don't think we can do any testing today, so I'll just go for a dummy. Okay. Dummy is just gonna be a list node. Doesn't really matter. And even head equals dummy, and node equals head. Okay. While we could end in even or odd, and I guess it's fine. Because I'm gonna move, this have to be next to next, right? So while node.next, yes, while node.next, because I want to take node.next. But when I move node.next.next. Interesting. You know what? I should just say while node. It's fine, right? And then we're gonna remove node.next. And we basically say, if we have a node.next, then we remove it, okay? So we say, if node.next, right? Then we're gonna remove it. How do we remove it? We say, let's actually say temp, okay? Temp equals node.next. If temp, okay? If not temp, well, if not temp, then we are ending. But it's okay. If temp, then we say node dot next shall equal to node dot next dot next, right? And then that's we're already linked, right? We're already linked. Then temp dot next shall equal to none. We cut it, and then even head dot next shall equal to temp. Yeah, I like to do it this way. So remove it, put it into to there, and then we're done, right? And then not even head, even node. Okay, even node, odd node. Yeah, this is how we're supposed to do. Odd node and this is even node, right? Dot next, and even node equals even node dot next, and And once we remove, we can say odd node equals odd node on next, because I already put the next, go to the next one. So I remove this, then we go to the next one. And if temp is nothing, then we go to the next one. This one will become none, right? Yeah, so we get out, and then get out. At the end, if it's odd numbers, right? At the odd numbers, if it's even number, right? What if it's even number? What if it's even number? Then we have this, and this will become none. Huh? Yeah, this will become none. So I think it should be right. Then what? Ooh, I will put into none. That is not fun. That is not fun at all. You know what? I need to break out before I go to none, and then I lose information, right? So basically what we say is here, if odd.next, then we do this, else we're gonna break. Okay, so this can be true, that's fine. And then break, because I need the odd node to point to the last node, not point to none, right? And then we can say odd node.next equals dummy.next, because dummy.next is that. And now we're going to return head. Okay, let's try this. I can introduce a couple. So test case 1, 2, 3, 4. 1, 2. Yeah, that's about it. If they all pass, then we will pass. Yep. Oh, I've done this before. Oh! Oh. Oh, shoot. It does say 0. Damn, man. Forgot to test that. There we go. All right, let's check what we did in the past. If not head, turn head. $328. Just delete. Right, that's what we do. Delete all the even nodes and add them to another list. And at the end, add this even node list to the end of odd node list. Yeah, that will be it. That's ON. Let's see. 40, 70 test cases. Yeah, that's what I did, but it seems to be easier, right? Even head, that's what I did. Even tail, yeah, that's fine, that's the same thing. Well, odd done next. Odd done next. Okay, that's fine. Okay. Okay. Nice. Nice. Yeah, it's the same idea. 70 test cases, so we have more test cases this time. 70, it's not as efficient, but it's the same solution. All right, I'll let it pass. I will let it pass. Okay, so consider this done. Let's go back to this. We need to do BFS, not BFS, DFS. Up until here is exactly the same. Okay, so we need to do DFS. Okay. DFS, we're just starting from this, and then we try to traverse through everything. Right, starting from here, we try to traverse everything, and then pick the smallest. Right, so we can have a self.result. Right, and then what do we have? We have a node, which is actually an integer, and visited. Right, there's going to be a set of integers. That's what I think, but we'll see. Because as you go, right, as you go, do you go back? You go here and then you go back. Yeah, because you're here. Do you go back? Nah. You need to get back, right? Because you have to cover all the edges. So we're gonna do the same thing. It's gonna be edges again. We'll push the edges in. All right, we push the edges in. Yeah, so we go to the next one, and then this is something we have visited, but we don't know if the edge has been visited. So you're saying we need to handle both. No. What we say is if you go to something that you have hit before, you record. You record the weight, but you don't add it. You see what I'm saying? Yeah, you see what I'm saying? And we don't actually return anything. Okay. So, given the current node, right, we are going just to go through the graph. Yeah, node. When you say visited, I'll add node. Right. And then for be this in graph node. Okay. I always check. Right, I always check. And then if B is not in visited, then DFS B visit. I don't even need to do visited. I don't even need it, right? Or just DFS B. And if B is in, then I don't go, but I already consider the distance. So we blah, 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 go through everything. So we go down here, right? We'll go one path. Once we're done, oh, we need to remove it. Because I might go down the other path. Hold on, let me think. I go down this path, I hit everything, right? And go down that path. Why do I... No, I think this should be right. Alright, and then we just call DFS1, and then we return self.res. Let's try. That is not right. Dict. It seems to be working. All right, We need to try this. Ooh. Ooh. Nope. Out. Solution. Okay. That's fine. I have to wait. So it won't time me out. Come on. I visit everything only once. Yeah. Seems to be right. Try this. Might take a while, but it's actually not bad. It's actually not too bad. It's not bad at all. Just DFS, right? Just traverse through everything, starting from 1, and pick up and keep track of the smallest edge. That's it. We call it ON. This is gonna be ON. Nah, this is not O. This is land roads, right? Yeah, this is slightly different. Okay, so that's all 3. Now we're done with this. Move on. Okay, what's this one? Divide nodes into the maximum number of groups. You're given a positive integer n, representing the number of nodes in an undirected graph. The nodes are labeled 1 to n. You are also given a 2D integer array edges, where edges, okay, indicates there exists a bidirectional edge between A and B. Notice that the given graph may be disconnected. Okay. Divide the nodes of the graph into m groups such that each node in the graph belongs to exactly one group. For every pair of nodes in the graph that are connected by an edge, if AI belongs to the group with index x and BI belongs to the group with index y, then y minus x equals 1. Return the maximum number of groups into which you can divide the nodes. Return -1 if it is not possible. The maximum number of groups. So 5 and 1 are connected, right? So 5 is belong to group 1, 1 belongs to group 2, so the difference between their group indices is 1, right? Difference between the group indices is 1. Difference between group indices. Difference between group. Very interesting. And you want a maximum. Wait, is the answer not deterministic? Alright, so why is this one's -1? So we have 1, 2, I just draw it out. We have 1 and 2, 2 and 3, and 3 and 1. Okay. So if 2 are connected, they must belong to 2 groups, right? If 2 are connected, they must belong to 2 groups. So 1 and 2 must belong to 2 groups. 2 and 3 must belong to 2 groups. And then 1 and 3 must belong to 2 groups. Okay? So that means each one has to be its own group. And if each one is its own group, and then we label it 1, 2, 3, and then 1 and 3 will be 2. Okay. Wow, looking awesome. And the pee. Yeah, I'm hungry.
Oh no, you're waiting for us?
No, Man, I have no idea. Man, these difficult questions are tough. Hold on. So, okay, again. All these has to be in separate groups, right? So we can just say, okay, we have 1 and 2. So 1 has to be, I mean, it's a graph, right? It's a graph, so we can traverse the graph from, where do we traverse the graph? Let's take this, instead of going from 5, how about we go from 3, right? If we go from 3, 3 go to 2, right? 2 goes to 1 and 6. And then 1 goes to 5, and 1 goes to 4, and 6 goes to 4. So, yeah, if we change it, it will be 3, 2, 1, 6, 4, and 5. If we do this, 3 is a group, 2 is a group, right? And 2 go, these two are a group, and these two are a group. So 1, 2, 3. That's 4 as well. Layers, right? Each layer is a group, right? Is that correct? And then yeah, each layer is a group. So is this asking us how many layers? And it's required that within the layer there are no connections within the layer. So I need to figure out one possibility where it's not 4. So 2 connects to 1, 3, 6. Okay? 1 connects to 5 and 4. 3 connects nothing. 6 connects to 4. So 6 connects to 4. I see. If I start from 2, if we pull it up from 2, and then we only have 3 layers. We have 1, 2, and 3. So the question is, how do you... It's like BFS, right? How do you BFS this graph such that, I mean, if it's multiple, it's fine. So how do you BFS the graph such that we have the maximum number of layers, and provided that there are no connection within the layer? I mean, can we just... That's going to time out, come on. But n equals to 500. Right? N equals 500. If n equals 500, I try starting from every single one. Right? I try from every single one, and just to count how many layers I can get. I mean, it's gonna go through 500 times, and 500 times 500. Maybe. Who knows? Maybe. Let's give it a shot. If it's wrong, then it's wrong. I mean, it's fine. We're not in the competition anyway. All right, let's try this. I'm just gonna brute force it. All right, just brute force it. We're gonna try from every single one and then count how many layers there's gonna be. And then we pick the largest layer. And, hold on. But you cannot just do that, because you have to also make sure that each layer, there are no connections within this layer. How do I make sure about that? Man, oh man, that's interesting. How do I make sure that... I mean, for each layer, I got all the nodes, right? And how do I know these nodes do not connect with each other? I mean, that's actually a good question. How do I know that there's no connection in the same row? Oh, I do know. So if I get the next layer, right? The next layer can be a set. We can actually do it as a set. It's not going to be a queue. It's going to be a set. And then we put the next nodes into the set. And then when we go for the next one, we see if the next one's inside the set. You see where I'm going, right? You see where I'm going with this? Yeah, from the start, I'm going to the next layer, right? That's fine. And then this next layer is going to be a set. And then for each one of these, we can obtain the next one, the next layer. But when you get the next layer, you will have to, because it can go backwards, right? So we have to prevent from go back. So we have visited and the same layer. So if it's inside the visited, now we just ignore it. If it's inside the same layer, then it's wrong. Okay, let's give it a shot. Okay, we have an idea, but first things first. Man, I just copy and paste this. Come on. There's no this. It's going to be A and B in edges. Graph A dot append B. Graph B dot append A. Okay, so that's the graph. Now we're gonna BFS res equal to 0, right? And the number of layers. So let's start with a layer 1. Okay. And we have n 1 to n. Okay, so for I in range, okay, 1 to n, node equal I, okay, q equals I. It's a set. It's a set. I mean, it's only 500, so even if we don't do the set, maybe it's fine. So, all right, it's okay. And we say levels, all right? Level is equal 1 because that's a start, and then we say while q temp is going to be a set and visited. Parents is going to be a set. Okay. Nah. So let's visited. Visited is going to be a set. Temp is here, and then we say for node in Q. Okay. If node not in visited. Where do you put? Yeah, I do the way I like. If node is in visited, we ignore because that's going backwards, right? If node is not in visited, right? If it's not in visited, you know what? Let's do level 0, and then we do level plus equal 1 here. Okay. If a node is not in visited, then we will say, you know what? Let's return -1. That actually should be -1. If node not in visited, and then we say if node is in, how do I break it? Well, we just break it. We need a sentinel, right? If this node is in temp. No, not in temp, in queue. Because the next node is in the same level. Impossible. Impossible equals false, right? So if node, then we say impossible is equal to true, and I'll break. Otherwise, if node is not in queue, wait, hold on, what you doing? No. For next node, in graph node, there, that's when we start. So for node everyone, and then each one has the next node. And we say if the next node is not invisited, if it's invisited, we'll keep going to the next one, keep going. And then if no node is in queue, then impossible can be true, then we're gonna break. Right? We're gonna break. So we break this thing. Okay, we break this thing, which means for this node, something is wrong. And if we break this thing, then we check, right? When I get out, we check. Hold on. So if it's in queue, which means the next one's in, so it's impossible. If it's not in queue, then we say temp.add next node. All right, blah, 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 blah. Once we're done for the current node, then we check. We say if impossible, then we break. Right? If impossible, then we break. If it's not, if it's still possible, then we will go to the next node. Go to the next node. Okay, next node. We try to fit out the next level, and the next level is done. Coming out again. If impossible, then break. Huh. It seems like impossible should be on the outside, because if one of them is impossible, then it's just gone. Right? If impossible, then we'll break. Otherwise, if it's possible, then q equals temp. We'll go to the next one. And I go to the next one, level plus equal 1, blah, blah, blah. Once I come out, we say if impossible, if not impossible, which means if it's possible, then res equals maximum, res and level. And then we keep going, now we return res. Or you have to go through everything. I don't know. If it's wrong, then we handle it later. I have to try this first. In edges. Magnificent sets, nice name. Oopsie doozy, what happened? No module collection. Oh, shoot, it's collections. Damn, what the hell happened? No way. Oh, something is wrong. While q, temp, right? Oh, we didn't say visited. Damn, visited. right. What happened? So why start from 1? Okay, enjoy. Right, if we start from 1, we're gonna have 2 and 3. Alright, so this is gonna be 2. 2 is not in visit. 2 is not in queue. So temp can have 2, visit have 2, temp have 3, visit have 3, right? Then queue equals the temp and I see. Should say if impossible, then level equals -1. Ooh, that is, well, this is right. So we have to reset. It's saying for this one is going to be impossible. But why is it still not right? Let's see, what queue do we have? 1, 2, 3. 2, 1, 3, 3, 1, 2. That's correct, right? So on 1 we have, and then we have 2, 3. Let's see the level. Test level is 1. Level is 2. Yeah. And then for node is 2. For NN in graph node, we'll have 1 and 3. If 1 is invisited, so 3. 3 is I have to put visitor somewhere else. Damn. Oh, it's okay. For each node, then we say visited.add node. So this will be this. Don't do it here. Yep, this one's right. We add a visit every time we visit it. Okay. So if I comment out this, okay. Now the question is this fast enough? Is this fast enough? Give it a shot. It's O(n) squared. That's what I bank on. Ay. I got a wrong answer. Output, what the hell? Did I pass any? Pass 28. That doesn't look nice. It does not look nice at all. The method itself is wrong. Supposed to have 57. What? Man, that's too much. That is way too much. Oh, I forgot it could be disjoint. God. All right. Okay. That's fine. Oof, disjoint. Man, oh man. Ooh. So you need to handle this joint. I mean, we can use union find to find out which one belongs to which. and then we just do within that. We can do that. That will be interesting. Okay. Yeah, let's try this. All right, let's write union find again. Parent. Rank. Okay. Parent x is not equal to x. Right. If py equals px, smaller k, and self dot rank parent px equals py, else rank px self dot parent py equals px. Okay, so with that, what we can do is dsu equals dsu n plus 1 actually, and then we go through the edges for a, b in edges, dsu dot union a and b. Okay, so once we're done, yeah, then we produce the graph. Okay, we have the graph. Now we have the result, and we need the result has to be zero, and then we just keep adding, right? Keep adding. So we're gonna have a def max height, max level. Okay, so we're gonna pass in is the nodes. It's gonna be a list of int, and I'm gonna return integer, and then I'm gonna do this entire thing, put it here. Rest is gonna be -1. Our range, that's not range. For I nodes, q visits, blah 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 blah. That's fine. Rest a blah blah blah. I'll return rest. Okay. Now what we need to do here, we have another rest, and then we have to go within each group. Right? And how do we know we have each group? Is using the DSU. So how do we do that? Well, I mean, we have to find everything again, so they will be the groups, groups. Okay, for I in range 1 to n plus 1, pi groups dsu dot find I dot append I. Okay, so that's we get a groups. And now what we're gonna do is for a g in groups dot values. Okay, and the max ml max level equals self dot max level. Nodes are gonna be g, all right. Current max level, and we say if current max level is equal to -1, it's not equal to -1, it's larger, it's not equal to -1. Okay, if it's not equal to -1, actually we can just we can do 0, right? We can do 0. It's okay, and then we just set it to 0, so it'll be 0, right? So we just res plus equal to self plus equal to current max level, right? And at the end, if it's 0, right, we're gonna return res if res is larger than 0, else we're gonna -1. And we can actually just do this right here. All right, let's try this. The graph is not defined. Oh shoot! We need a graph. Graph is gonna dict of integer and a list of integers. So we need a dict. And we need to pass graph. There we go. That's the reason. Yep. So we just need a DSU. Let's put it in, just, you know, safety. Okay. Try that. Doesn't look nice. Oh, shoot. I think I know. I think I know why. Damn. Hold on. I think I know why. Man, this turned into just trial and error. I hate it. It shall be anything is -1, right? So current max level. Say if current max level is equal to -1, which means one of them cannot do, we shall return -1. Otherwise, res plus equal to current max level. Then we can just return res. No. Oh, what should be 0? If not, which means not possible to form magnificent sets with G. There we go. That's it. This is the stuff. This is the stuff. I mean, in this case, we can actually do -1, right? Yeah, we can actually do -1 here. So it'll be consistent on both sides. It'll be -1. So we can just say if this is equal to -1, then we'll just return. Yeah, it still works. Okay, I have something. This is looking too terrible, right? Can we make it better? And break, right? So we break. Because it's this and then break. If we say else, so it'll be like what? So instead of this, we say for this, not visited. If it's in queue, then we'll break it, right? We don't do this, then we break. When we break, then we have else, just continue. Alright, else, that means this one all done. We'll continue the next one. Otherwise, we'll break. And then this one's the same. This is this. We can say else. Right, we'll say continue. Else is not continue, so else is gonna be this and then continue. If it's not else, then we break. Right? And coming out, we say else is going to be this and continue. Otherwise, we'll break. Let's see. Yep, I think it works, and I like it better. It doesn't really make it simpler, but we can remove one element. Always nice to remove one element, man. Always nice. Yeah. All right. Final solution. Go. Got it. Got it. Would I be able to solve this in time? How much time it took? 40 minutes today? 30, 40? Yeah, actually, I think if I had done the contest on Saturday, I might have actually finished off all of them. But this is considerably easier than some of the difficult questions I've done before. So yeah. All right, so the problem can be converted to finding the maximum level or height, right, of a graph. Given that n is smaller or equal to 500, we can choose any node as the starting node, right, as starting node, and run BFS to find the max height, the max level we can reach in that configuration. Two tricky parts. First, at each level, we have to also make sure that first we have to make sure that none of the nodes on the same level connect with each other, right? None of them connect with each other. If there is connection, this configuration is impossible. And once that is impossible, right? 2, since the graph can be disconnected, we need to run the BFS on each connected, I think it's called click, and add the max levels of all the clicks together. Now, the caveat is that if one click is impossible to form magnificent sets, and we must return -1 immediately. Now, to find all the clicks, we can use our best friend, binary union find. I don't know the runtime. I mean the runtime, I'll call it O(n squared, because this takes O(n squared to run. The max level takes O(n squared to run. All right, let's take a look at discussion. Bipartite check. BFS union. People write the exact same thing. Huh? Oh, we can actually find the depth. Oh, maybe DFS is easier. I forgot, what does bipartite mean? The number of groups we can create for a connected graph is the maximum of minimum distance between all nodes in that graph. Yes. Number of nodes in the path. No, union find is much easier. Yes. We need to check if there is an odd number edge cycle in the graph. Oh. Okay, this I don't understand. Do a BFS can start. One thing we have to do is check it has odd number edge cycle. if the neighbor node has been visited before. If the neighbor node has been visited before, and if the neighbor was on the same level as the current node when we are visiting them. They use level. They use level. I see what you did there. They use level. Not in scene. We add. So that's scene. Okay, we add the level of the scene, and then we do. If it's in scene. And we check if the level. I see. That's another way, right? Not the natural way that I had thought, but man, look at this. It's so much easier. Why? All this. You could have just returned -1. Come on. We'll just return -1. And then none of these things will matter. Right? And we just do regular. Holy crap. Don't need any of this. Yeah, why don't you just return? And we can do, it doesn't really matter what we start with. Yeah, it still works. Damn. Could have just returned it. Right? Much easier. While Q, I have a 4. But why I have 2 4? I don't have 1 4. Oh, because it's a use pop left. That's why. It's alright. It's the same thing. Alright. Okay, so yeah, that's that. We can do BFS. That's the same thing. BFS to find a connected component. Yeah, that's true. Well, we can use, I'm too lazy. I am too lazy for this. DSU is so much easier. I don't even have to go through my mind, and then, boom, done. But we do have to do the groups though. This will naturally handle the group. It's alright. Alright, that will be it. See you guys.